Hello everyone. Today we will study Lagrange multiplier. Before I introduce what is the Lagrange multipliers, first of all, let's keep this idea in mind. Note, in general, we use the Lagrange multipliers to find absolute maximum and absolute minimum of a function. With some constraints. First of all, let's review a problem from your first semester calculus class about absolute maximum and absolute minimum. Let's review this old problem first. Let x and y be two positive numbers. If their product x times y is 100, what is the smallest possible value that their sum x plus y could be? If x and y are two positive numbers and their product is 100, what is the smallest possible value that their sum could be? In this problem, we give the product x times y is 100. We give this product as a condition, and we try to find the minimum value of their sum. In general, if we treat x times y as a function of as a two variable function, if we treat this as a two variable function, we have g of sy equal to 100. G of sy equal to x times y equal to 100. This function is called the constraint function. We give this function as a condition. This is called constraint function. We give this function g as a condition. This is called constraint function. And the value we are looking for is x plus y. This is also a two variable expression. If we treat this as a function, f of sy equal to x plus y, then that's the function we try to minimize or maximize. This function is called the objective function. So the expression given as a condition is called constraint function, and the expression we try to maximize or minimize is called objective function. Now let's solve this problem using the old technique. Let's solve this problem using old technique. If we use the old technique, we first of all solve the constraint equation with get y by itself. We first of all solve the constraint equation, get y by itself. we have y equal to 100 over x. Then we plug in y into an objective function. We are looking for the sum. The sum is x plus y. Y is 100 over x. So we have x plus 100 over x. And x and y, since x and y they are positive numbers, x must be strictly greater than 0. This function s is a single variable function called s of x that can be rewritten as 100x raised to -1. In order to find maximum, minimum, we take derivative. I have 1 minus 100x raised to -2. If I simplify, it can be rewritten as x squared minus 100 over x squared. Then, in order to find critical point, we set the function equal to 0. When a fraction is 0, its numerator must be 0. When a fraction is 0, its numerator must be 0. X squared minus 100 equal to 0. If I solve for x, s equal to x squared equal to 100. S equal to positive 10 and -10. And since x is always positive, we reject -10, so x must be positive 10. Next, use number line test to verify, if this 10 is an absolute maximum. Next, we use number line test to verify if this x is an absolute maximum. Since x can only be positive, we start from 0. 10 is a critical point. We pick test number between 0 and 10, say 5. Pick test number greater than 10, say 20, make it easier. Then we plug in each test number into the derivative. If I plug in 5, 5 squared is 25. 25 minus 100 is negative. 5 squared is 25, which is positive. Negative number over positive number is negative. If the derivative is negative, it means the function is decreasing. If we plug in 20, 20 squared minus 100 is 300. And the bottom, 20 squared is 400. 300 minus 400 is positive. So if the derivative is positive, function is increasing. So we have a minimum at s equal to 10. Since the function goes down and turn over at 10, this is 10. There's a turning point at 10. And this 10 is an absolute minimum. There's a 10. At s equal to 10, there's an absolute minimum. This is a turning point. The curve goes down and turn over. This is an absolute minimum. So we have an absolute minimum at s equal to 10. When s equal to 10, y is 100 over 10, which is also 10. So when s equal to 10, y equal to 10, their sum is the absolute minimum. Their sum is 20. 20 is an absolute minimum. So the smallest possible value of their sum is 20. Next, let me show you a different way to find the absolute maximum and absolute minimum. In this old example, the constraint function g of sy equal to 100. I can consider this as a level curve. So I can consider g of sy equal to k as a level curve. Now, for an objective function, f of sy, if I let f of sy equal to c, then by choosing different value for c, say c equal to 1, 2, 3, and so on, by choosing different value for c, I can also draw level curves for f and g. Now let me show you the picture. In the sy plane. Say the constraint g of sy equal to k is some curve, for example. That's the constraint g of sy equal to k. Now for function f, say when c equal to 1, that's my level curve. When c equal to 1, for example, f of sy equal to 1. When c equal to 2, that's my level curve, for example. When c equal to 3, that's my level curve. F of sy equal to 3. When c equal to 4, that's my level curve. F of sy equal to 4. F of sy equal to 5. F of sy equal to 6. F of sy equal to 7. F of sy equal to 8. F of sy equal to 9. F of sy equal to 10. Now here we can see that the level curve when c equal to 4, 5, when c equal to 4, 5, 6, 7, 8, when c equal to 4, 5, 6, 7, 8, the level curve of f intersects the level curve of g. When c equal to 4, the level curve of f intersects the level curve of g at these 2 points. When c equal to 5, the level curve of f intersects the level curve of g at these 2 points. So when c equal to 4, 5, 6, 7, 8, we can see that the level curve of f intersects the level curve of g. And when c equal to 1, 2, 3, when c equal to 9 and 10, the level curve of f doesn't intersect the level curve of g. Now, since we are looking for the maximum value and the minimum value of f under the constraint g of sy equal to k, and f of sy actually equal to c, that means we are looking for the largest and the smallest value of c. We are looking for the largest and the smallest value of c, such that the level curve of f intersects the level curve of g. So we are actually looking for the largest possible c value and the largest and the smallest possible c value, that level curve of f intersects level curve of g. Now, for example, suppose say when c equal to 3.6, for example, when c equal to 3.6, the level curve f of sy equal to 3.6 tangent to the level curve of g at point P, for example. When c equal to 3.6, the level curve of f tangent to the level curve of g at point P. And when c equal to say 8.5, when c equal to 8.5, the level curve of f tangent to the level curve of g So when c equal to 8.5, the level curve f of sy equal to 8.5. Tangent to the level curve of G at point Q. That means the largest and the smallest f, the minimum and the maximum value of f under the constraint G of sy equal to k is 3.6 and 8.5. That means the largest and the smallest value of f under the constraint G of sy equal to k is 8.5 and 3.6. And the maximum value of f occurs at point Q. The minimum value of f occurs at point P. So in this example, assume when c equal to 3.6, the level curve f of sy equal to 3.6. Tangent to the level curve G of sy equal to k at point P. And when c equal to 8.5, the level curve f of sy equal to 8.5. Tangent to the level curve G of sy equal to k at point Q. Then we can see that f has a minimum 3.6 at point P. F has a maximum 8.5 at point Q. Then we can see that f of sy has its minimum at P and its maximum at Q. Let's look at these 2 points P and Q here. Let's look at these 2 points P and Q. At point P and point Q, the level curve of F tangent to the level curve of G. If two lines tangent to each other, what does it mean? If two curves tangent to each other, that means they have the same tangent line at this point. At point P, if the level curve of F and the level curve of G tangent to each other, that means they have the same tangent line at point P. If two curves tangent to each other, that means they have the same tangent line. Same thing here, since at point Q, level curve of F and G tangent to each other, they also have the same tangent line at point Q. Next, I would like to remind you one thing that we learned in section 11.6. Let f of sy equal to k be a level curve, any kind of level curve. Then, for all point P on the level curve, the gradient vector at point P the gradient vector at point P always perpendicular to the tangent line at point P. The gradient vector in point P always perpendicular to the tangent line at point P. So let f of sy equal to k be a level curve. Then for all points P on a level curve, the gradient vector at point P is always perpendicular to the tangent line at point P. Now, let's go back to this old problem here. We know that at point P, the level curve of f and the level curve of g, they tangent to each other, which means they share the same tangent line at point P. But we know that for any level curve, the gradient vector is always perpendicular to the tangent line. So at point P, the gradient vector of f and g, they both perpendicular to the common tangent line. Gradient of f and the gradient of g, they both perpendicular to the common tangent line. That means they must be parallel to each other. That means at point P, the gradient vector of f and the gradient vector of g must be parallel to each other. And similarly, at point Q, level curve of f and level curve of g, they tangent to each other. That means they share the same tangent line. Since the gradient vectors are perpendicular to any level curves at point Q, since the gradient vectors are perpendicular to both level curves at point Q, then the gradient vector of f and g must be perpendicular to the common tangent line at point P. The gradient vectors of f and g, they must be perpendicular to the common tangent line at point Q. Therefore, the gradient vector of f and the gradient vector of g must be parallel to each other. So in both cases, the gradient vector of f and the gradient vector of g, they must be parallel to each other at point P and point Q. So when there is a maximum and there is a minimum, when there is a maximum at P, when there is a minimum at Q, the gradient vectors of f and g must be parallel to each other. If they are parallel, they must be multiples of each other. If they are parallel, they must be multiples of each other. So in this particular example, at points P and Q, the gradient vector of f must be a multiple of the gradient vector of g. Since they are parallel, they must be multiple of each other. And this lambda has a name. It's called Lagrange multiplier. This lambda has a name. It's called Lagrange multiplier. Next, let me introduce the method of Lagrange multiplier. To find the maximum and the minimum value of f of sy. Subject to the constraint g of sy equal to k, we need to solve the equations that gradient of f equal to lambda times gradient of g and g of sy equal to k. The reason we are solving this equation is because at the maximum and minimum point, gradient of f must be parallel to gradient of g. If they are parallel, then gradient of f must be constant multiples of gradient of g. So at maximum and minimum point, gradient of f must be constant multiple of gradient of g. That's the reason we solve the first equation. For the second equation, we are solving for g of sy equal to k. It's because every maximum minimum point must locate at the level curve g of sy equal to k. So both of them must satisfy this equation g of sy equal to k. That's why we have to solve the equation g of sy equal to k. Then solve both equations. We find all potential maximum and minimum points. Their solutions are called potential maximum and minimum points. Then we substitute each potential point into the original function f of sy. Then the largest is the absolute maximum and the smallest is called the absolute minimum. The same ideas also work for functions with 3 or more variables. If there are 3 variables, g of syz, f of syz equal to c, g of syz equal to k, the level surface for g of syz equal to k, this is a level surface instead of level curve, it will be a level surface here. Then for c equal to 1, 2, 3, we have multiple level surfaces. When two level surfaces tangent to each other, in the condition that two level surfaces tangent to each other, they must share the same tangent plane. If two level surfaces share the same tangent plane, then since the gradient vector is always the normal vector of the tangent plane, since the gradient vector is always the normal vector of the tangent plane, both gradient vector must be perpendicular to the tangent plane. If both gradient vector perpendicular to the tangent plane, to the same tangent plane, they must be parallel to each other. So we also have gradient of f equal to lambda times gradient of g at every maximum and minimum point. That's why this idea works for functions with 3 or more variables. This method works for functions with 3 or more variables. Now, let's go back. Look at the first problem we did in the beginning of the class. Let's redo this problem. In this problem, we have a constraint function g of sy equal to 100. Objective function is f of sy equal to s plus y. So let's use Lagrange multiplier for this problem. We want to set gradient of f equal to lambda times gradient of g. What's gradient of f? Gradient vector of f is f sub x comma f sub y. If I take partial derivative with respect to x, in function f, if I take partial derivative with respect to x, I get 1. If I take partial derivative with respect to y, I also get 1. Now what's gradient of g? Gradient of g is partial derivative of g with respect to x and partial derivative of g with respect to y. What's partial derivative of g with respect to x? In this function, if I take derivative with respect to x, I get y. In function g, if I take derivative with respect to y, I get x. Then use the formula here. 1 equal to lambda times y. 1 equal to lambda times y. And the other one equal to lambda times x. Together with the constraint x, y equal to 100. We have 3 equations with 3 variables. We have 3 equations with 3 variables. Solve the equation for s, y, and lambda. How can we solve this equation here? We can try to use we can try to eliminate some variable first. If I multiply first equation by x, I get x equal to lambda sy. If I multiply second equation by y, I have y equal to lambda times xy. Then if I combine these two equations, x equal to lambda times xy, x equal to lambda times x times y also equal to lambda times x times y. If I combine these two equations together, that means actually s equal to y. Since x and y is the same, I can substitute into the third equation. Since s and y is the same, I can substitute into the third equation. I have x times x equal to 100. Since s, y is the same, I can replace y with x. I have x times x equal to 100. S squared equal to 100. Since we only consider positive integer, x must be 10. Solve the equation, we get x equal to 10. And once we know x, we can try to solve for y. Xy is 100. I substitute 10 for x. Solve for y. Y equal to 10. So that's one of the potential points. X equal to 10, y equal to 10. Then we plug in s and y into function f. To verify if it's a maximum or minimum. So make table. If I substitute x and y, I get 20. But if there's only one number, how do we know this is a maximum or minimum? If there's only one number, how do we know if this is a maximum or minimum? So in order to verify if this is a maximum or minimum, we try to plug in a different value, point to verify. If I plug in a different point, I find a larger value, that means this must be a minimum. If I plug in a different value here, I find a smaller value, then this must be a maximum. So we need to plug in a different point. If I plug in a different point, this value is larger, then this must be a maximum. If I plug in a different value, this is smaller, then this must be a minimum. So let's plug in a different point that satisfies the constraint. Let's plug in a different point that satisfies the constraint. If I plug in, say, 5 times 20 is also 100. 5 times 20 is also 100. So if I plug in a test point, if I plug in a test point 5, 20, if I plug in a test point 5 times 5 and 20, I plug in 5 and 20 for s and y. I plug in 5 and 20 into the objective function. 5 plus 20 is 25. The test number is larger. That means this must be a minimum. Since the test point is larger, this must be a minimum. And since this is a test point, it doesn't count as a maximum. This is not a maximum. There's no maximum here. The minimum is 20. And we have the same conclusion using the old technique. We get the same answer using the old technique. Let's look at more examples about Lagrange multiplier. First one, find the maximum and the minimum value of function f of sy equal to x times y on the ellipse x squared plus 4y squared equal to 8. In this problem, since we try to find the maximum minimum of the ellipse, we treat this ellipse as the constraint. So this is the constraint. Then we apply Lagrange multiplier here. We try to set gradient of f equal to lambda times gradient of g. For gradient of f, we take partial derivative of f with respect to x and with respect to y. If I take partial derivative with respect to x, I get y. If I take partial derivative with respect to y, I get x. For gradient of g, if I take partial derivative with respect to x, I get 2x. If I take partial derivative with respect to y, I get ay multiplied by lambda. Set them equal to each other. Then this can be rewritten as y equal to 2 lambda x equal to a lambda y. Then together with the constraint x squared plus 4y equal to 8, we try to solve 3 equations for 3 variables. So usually we can try to eliminate some variable first. If I multiply the first equation by 4y, I will have 4y squared equal to a lambda sy. If I multiply second equation by x, I have s squared equal to a lambda sy. Then if I combine these 2 equations together, 4y squared equal to s squared, because they both equal to a lambda sy. So if I combine these 2 equations together, I have 4y squared equal to x squared. If I combine these 2 equations, I have 4y squared equal to s squared. Then I can substitute x squared into the last equation. So I have s squared equal to 4y squared. I have 4y squared plus 4y squared equal to 8, which means ay squared equal to 8. If I divide both sides by 8, y squared is 1. So y equal to plus minus 1. If I substitute y here, y squared is 1. If I substitute y squared here, I have 4 times 1 equal to s squared, because y squared is 1. 4 times 1 equal to s squared. X squared equal to 4. So s equal to plus minus 2. Therefore, we have 4 points here. We have 4 solutions here. For s and y, we have 4 solutions. S equal to 1, x equal to 2, y equal to 1. S equal to 2, y equal to negative 1. S equal to negative 2, y equal to positive 1. S equal to negative 2, y equal to negative 1. Then plugging each potential answer, each potential point into function f. Plugging each point into function f. 2 times 1 is 2. 2 times negative 1 is negative 2. Negative 2 times 1 is negative 2. Negative 2 times negative 1 is positive 2. So the largest is absolute maximum, the smallest is absolute minimum. So here, absolute maximum is 2. Absolute minimum is negative 2. Next example, find the minimum value of f of syz equal to 2s squared plus y squared plus 3z squared. Subject to the constraint 2x minus 3y minus 4z equal to 49. Here in this problem, function f is an objective function, and this equation here is a constraint. Usually we consider the constraint as a function of g, and it has 3 variables. We consider this is g of s, y, z. In order to find the minimum value for function f, we can use Lagrange multiplier. So gradient vector of function f equal to lambda times gradient vector of function g. For gradient vectors of function f and g, we take partial derivatives with respect to x, y, and z. So let's take partial derivative for function f first. I get 4x, 2y, and 6z. Keep lambda the same. Gradient vector of function g is 2, -3, and -4. So these equations can be rewritten as 4s equal to 2 lambda, 2y equal to -3 lambda, 6z equal to -4 lambda. Together with the constraint equation, 2x minus 3y minus 4z equal to 49. We have 4 equations with 4 unknowns. We can solve this 4 equation for these 4 unknowns. How do we solve this equation for s, y, z, and lambda? In the first equation, if I solve for x, I can write x as lambda over 2. In the second equation, if I solve for y, I can write y equal to -3 over 2 lambda. In the third equation, if I solve for z, I can write z equal to -2 over 3 lambda. Then I can substitute x, y, and z into the last equation and solve for lambda. If I substitute x, I get 2 times lambda over 2. If I substitute y, I get -3 times -3 over 2 lambda. If I substitute z, I get -4 times -2 over 3 lambda equal to 49. Then simplify each term individually. I have lambda plus 9 over 2 lambda plus 8 over 3 lambda equal to 49. And here you can see that the least common denominator is 6. The least common denominator is 6. So I can multiply both sides by 6. So if I multiply left side by 6, I get 6 lambda plus 27 lambda plus 16 lambda. On the right side, if I multiply right side by 6, I got 49 times 6. I don't know what it is. Let's leave it for now. On the left side, if I combine like terms, 6 plus 27 is 33. 33 plus 19 is 49. I get 49 lambda equal to 49 times 6. If I divide both sides by 49, I got lambda equal to 6. Once I know lambda, I can plug in lambda, find s, y, and z. So x equal to 6 over 2, which is 3. Y equal to -3 over 2 times 6, which is -9. Z equal to -2 over 3 times 6, which is -4. So the critical point here is 3, -9, -4. This is a potential maximum or minimum point. This is a potential maximum or minimum point. But if there's only one point, we can't tell it's a maximum or minimum. If there's only one point, we can't tell if this is a maximum or minimum. So in order to decide is this a maximum or minimum, we need to find a testing point. How do we find a testing point? We must find a point that satisfies the constraint. We need to find a point that satisfies the constraint. In the constraint here, if I substitute 0 for z, 1 for y, I can solve for x. In the constraint, if I let y equal to 1, z equal to 0, I can solve for x. 2x minus 3 times 1 minus 4 times 0 equal to 49. Then 2s equal to 52. S equal to 26. So testing point is 26, 1, and 0. That's a testing point. That's a testing point. Then plug in the critical point and testing point into function f. Critical point is 3, -9, -4. Testing point is 26, 1, and 0. If I plug in the first point, 3, negative 9, negative 4 into function f, I get 147 using my calculator. If I plug in the second point, 26, 1 and 0 into function f, I get 1353. So for these two numbers, 147 is smaller, so that's the minimum. The other number, 1353, is larger, but this is not a maximum, because this point, 2610, is a testing point. A test point doesn't count. This is a test point. Test point doesn't count as a maximum or minimum. So for function f, under this constraint, there's only one minimum value, 147. There's no maximum value under this constraint. That's the example. Find three numbers whose sum is 9. And whose sum of squares is a minimum. So first of all, let's find out what's the constraint function and what's an objective function. Here, the constraint is the sum equal to 9. Here, the constraint is the sum equal to 9. Suppose three numbers are s, y, z. The sum is 9, is the constraint. G of s, y, z equal to s plus y plus z equal to 9. That's the constraint. And what's an objective function? What we are looking for is that whose sum of squares is a minimum. The sum of a square can be written as s squared plus y squared plus z squared. That represents the sum of squares. So that's an objective function. The function we try to maximize or minimize is called an objective function. Here, since we try to minimize the sum, then this is the objective function. Next, we use Lagrange multiplier to solve this problem. Set gradient of f equal to lambda times gradient of g. Let's first of all find the gradient of f. Gradient vector of f is 2x, 2y, 2z. That equal to lambda times gradient of g. Next, let's find the gradient vector of g. Take partial derivative with respect to s, y, z. I have 1, 1, 1. Then that can be rewritten as 2x equal to lambda, 2y equal to lambda, 2z equal to lambda. The constraint equation is x plus y plus z equal to 9. Then solve this full equation for 4 variables. If we observe the first 3 equations, we can see that 2x equal to lambda, 2y equal to lambda, 2z equal to lambda. That means they are all the same. So combine first 3 equations together, we have 2x equal to 2y equal to 2z. Then I can divide each equation, each part by 2. I have s equal to y equal to z. That means s, y, z, they are all the same. If they are all the same, I plug in s, y, z into the last equation, into the constraint equation. I have x plus x equal to 9, since they are all the same. That means 3x equal to 9, s equal to 3. Since s, y, z must be the same, so we have s equal to 3, y equal to 3, z equal to 3. So that's the potential maximum or minimum point. Plug in. Plugging s, y, z into function f. If I plug in 3, 3, 3 into function f, I have 3 squared plus 3 squared plus 3 squared, that's 27. If we only find one value here, we can't tell this is a maximum or minimum. So in this case, we need to find a test point that satisfies the constraint. We need to find a test point that satisfies the constraint. For the test point that satisfies the constraint, I can use 2, 2, 5. 2, 2, 5 is a test point that satisfies the constraint. If I plug in 2, 2, 5 into function f, I have 2 squared plus 2 squared plus 5 squared. 4 plus 4 is 8, 8 plus 25 is 33. If the value at a test point is larger, that means this must be an absolute minimum. If the test point is smaller, this will be absolute maximum. Since the test point is larger, this is an absolute minimum. So that answers the question. The three numbers are 3, 3, 3, whose sum is 9, and the sum of the square is a minimum. Next example. Find the minimum distance from the surface z equal to square root of x squared plus y squared to point -6, 4, 0. First of all, let's determine what's the constraint and what's the objective function. In this problem, we're looking for minimum distance from the surface to a point. That means we are looking for points on the surface that give you minimum distance to this point. So since we are looking for points on this surface must be the constraint. This surface must be the constraint. So for the constraint, we try to put it in the form of g of s, y, z equal to k. We try to put this surface in the form of g of s, y, z equal to k. So I can rewrite this equation as, I can square both sides. Rewrite this equation as x squared equal z squared equal to s squared plus y squared, and move z squared over. I have s squared plus y squared minus z squared equal to 0. So I can write g of s, y, z equal to s squared plus y squared minus z squared equal to 0. So that's my constraint equation. Next, what's my objective function? We are looking for minimum distance from the surface to a point. Since we are looking for the minimum distance, so the distance will be my objective function. Distance from a point between 2 points. Distance from a point on the surface to this point, let's use distance formula. Distance from syz to point -6, 4, 0. For distance between 2 points, we can use s2 minus s1, y2 minus y1 over plus z2 minus z1 squared. So x2 minus s1 squared plus y2 minus y1 squared plus z2 minus z1 squared. I can rewrite this as square root of x plus 6 squared plus y minus 4 squared plus z squared. If I treat this as my f, then when I find the gradient, it's very hard. If I treat this as f, when I'm finding the gradient vector, it's very hard. It's very hard to take partial derivatives. It's very hard to take partial derivative with square root. To make it a little easier, I can square both sides. I make d squared to be x plus 6 squared plus y minus 4 squared plus z squared. If I treat this as my objective function, I can try to find the maximum or minimum of d squared. Since d represents the distance, it's always positive. The maximum of d occurs when d squared has maximum. Maximum of d or minimum of d occurs when d squared has a maximum or minimum. Since d is always positive, the larger d squared, and the smaller d squared. So the maximum or minimum of D occurs when D squared has a maximum or minimum. So if I treat D squared as my objective function, it will be much easier. It's easier to find a partial derivative without square root. Now let's use Lagrange multiplier. Gradient of f equal to lambda times gradient of g. We first of all take partial derivative for x of f with respect to x, y, and z. I have 2 times x plus 6, 2 times y minus 4, and 2z. Take gradient, find a gradient vector for g. Find a gradient vector for g. I have 2x, 2y, negative 2z. Then multiply by lambda. To make it a little easier, I can divide each equation by 2. Make it a little easier, I can divide each equation by 2. So I have x plus 6 equal to lambda x, y minus 4 equal to lambda y, z equal to negative lambda z. I divide each equation by 2 on both sides. Then together with the constraint, we have x squared plus y squared minus z squared equal to 0. Now we have 2 equations, and we can solve for, we have 4 equations, we can solve for 4 variables. The third equation, that looks like that's the simplest one. That looks like that's the simplest equation. If I solve this equation, what do I have? I can move lambda z to the other side. Z plus lambda z equal to 0. I can factor z out. Z times 1 plus lambda equal to 0. That means either z equal to 0 or lambda equal to negative 1. When z is 0, what do we have? When z is 0, we plug in 0 into the third equation here. We have x squared plus y squared equal to 0. Since the sum of perfect square is 0, both of them must be 0. Since they are both non-negative terms, if the sum is 0, they both must be 0. So s equal to 0, y equal to 0. That's one of the points that has potential maximum or minimum. When lambda equal to negative 1, I can substitute negative 1 into the first equation. I have x plus 6 equal to negative x. Then solve an equation for x. I have 6 equal to negative 2x, s equal to negative 3. If I substitute lambda equal to negative 1 into the second equation, I have y minus 4 equal to negative lambda equal to negative y. Then negative 4 equal to negative 2y, y equal to 2. So here I find x and y. Once I find x and y, I can substitute here to solve for z. x squared plus y squared minus z squared equal to 0. If I substitute x and y, I have negative 3 squared plus 2 squared minus z squared equal to 0. So I have 9 plus 4 equal to z squared. Z squared equal to 13. Since z is always positive, z equal to square root of x squared plus y squared, z is always positive. When I take square root, z is positive square root of 13. So that gives me another critical point. Give me another point with potential maximum and minimum. It's negative 3, 2, and square root of 13. Then plug in these 2 points into function f. plug these 2 points into function f. S, Y, Z. F of S, Y, Z. If I plug in 0, 0, 0, I get 0. No, I don't get 1 second. If I plug in 0, 0, 0, I plug in here. 0 plus 6 is 6 square. 0 minus 4 is negative 4 square plus 0. 6 square is 36. And negative 4 square is 16. 36 plus 16 is 52. If I plug in negative 3, comma 2, comma vertical 13, what do we have? I plug in negative 3 here. Negative 3 plus 6 is 3. 3 square is 9. 2 minus 4 is negative 2. Negative 2 square is 4. 9 plus 4 is 13. If I plug in vertical 13, vertical 13 square is 13. 13 plus 13 is 26. Now, it looks like this is the minimum. And this is the maximum. Does the answer make sense to you? Doesn't the answer make sense to you? This graph is a cone. This graph is a cone. Distance from a point to a cone. We can find the minimum distance. Minimum distance makes sense. Could we have a maximum distance? If we're looking for distance from a point to a cone, the cone is unbounded. It goes up to infinity. Can we have a maximum distance? It looks impossible, right? It looks impossible that we have a maximum distance from a point to a cone. The cone is unbounded. The cone is unbounded. Go up to infinity. The cone is unbounded. Go up to infinity. So it's impossible for us to have a maximum distance. Then what's wrong here? This is not a maximum. What's wrong here? Be very, very, very careful. This graph is a cone. At 0, 0, 0, 0, 0, 0, locate at the vertex of the cone. 0, 0, 0, locate at the vertex of a cone. That's a sharp angle. That's a sharp angle. At a sharp angle, the surface is not differentiable. At a sharp angle, the surface is not differentiable. The gradient of G does not exist at the sharp angle in the vertex 0, 0, 0. That's why this point is not the maximum. This point is not the absolute maximum. We can test it out very easily. Let's pick a point. Let's satisfy the constraint. So if I let s equal to 10, y equal to 10, 10 square plus 10 square, 10 square plus 10 square is 200. So I can pick a point that s equal to 10, y equal to 10, z equal to square root of 200. That's a test point. If I plug in the test point into function f, I have 10 plus 6 is 16 square. 10 plus 6 is 16. 16 square is 256. 10 minus 4 is 6. 6 square is 36. 256 plus 36 is 292. If I plug in vertical 200, when I square is 200. So 292 plus 200 is 492. Here you can see that at point 10, 10, vertical 200, under the same constraint, function f has a larger value than the value at point 0, 0, 0. That means at point 0, 0, 0, function f doesn't have an absolute maximum. So be very, very careful. When we use Lagrange multiplier and solve the equation, if in a solution either function f or g is not differentiable, then there's no guarantee that at this point it has an absolute maximum or absolute minimum. So be very, very careful. Now, let's answer this question here. Find the minimum distance from the surface to the point. Here, our f represents d squared. So know that the minimum value for f is 26. That means the minimum value for d squared is 26. So for the minimum value of d, we take square root. I get square root of 26. So that's the minimum distance from the surface to the point. Next example. Find the dimension of a box with volume 64 cubic centimeter and the surface area is a minimum. Find the dimension of a box with volume 64 cubic centimeter and the surface area is a minimum. So first of all, let's find out what's the constraint and what's the objective function. We know that the volume of the box is 64. Assume the length and the width and the height is SYZ. Assume the length, width of the box, length, width, and the height of the box is SYZ. If the volume is 64, that means the length times the width times the z must be 64. So that's the constraint. Let's call this g of SYZ. That's the constraint. What's an objective function? We are looking for the minimum surface area. So that means the surface area of the box will be the objective function. Since we try to minimize the surface area, it will be the objective function. So the objective function is the surface area. Surface area of a rectangular box is twice the length times width plus twice the length times the height plus twice the width times the height. That's the formula for surface area. Next, let's apply Lagrange multiplier for this problem. The formula is gradient of f equal to lambda times gradient vector of g. Let's first of all find the gradient vector for f. Take partial derivative with respect to x. I have 2y plus 2z. Next, take partial derivative with respect to y. I have 2x plus 2z. Next, take partial derivative with respect to z. I have 2x plus 2y equal to lambda times gradient vector of g. Next, let's find the gradient vector for g. If I take partial derivative with respect to x, I have yz. If I take partial derivative with respect to y, I have xz. If I take partial derivative with respect to z, I have sy. And together with the constraint equation, we have 4 equations and we can solve for 4 variables. Here we have 4 variables, 4 equations, we can solve for 4 variables. Solve these equations, this system of equations for SYZ and lambda. Let's try to eliminate something first. If I multiply first equation by x, I can make 2sy plus 2xz equal to lambda times xyz. If I multiply the second equation by y, I can make 2sy plus 2yz equal to lambda syz. if I multiply the third equation by z, I can make 2sz plus 2yz equal to lambda times syz. Now you can see that all these expressions, they all equal to lambda syz. So if I set the first equation equal to the second equation, I have. If I set the first equation equal to the second equation, I have 2sy plus 2xz equal to 2sy plus 2yz. I can cancel 2sy from both sides. I have 2xz equal to 2yz. Since s times y times z is 64, that means syz, none of them can be 0. They are not zeros. If the product of syz is not 0, that means none of syz could be 0. Since z is not 0, I can divide both sides by 2z. Since z is not 0, I can divide both sides by 2z. If I divide both sides by 2z, I have s equal to y. Now, since the second equation and the third equation are also equal to lambda syz, if I set the second equation equal to the third equation, what do I have? I have 2sy plus 2yz equal to 2xz plus 2yz. And we can see that 2yz on both sides are cancelled. I have 2sy equal to 2xz. Since syz cannot be 0, I can divide both sides by 2x. So I get y equal to z. Since s equal to y equal to z, that means s must equal to y and s must equal to y and equal to z. So s, y, z, they must be the same. Then since they are the same, I can plug into the third equation. So I have x times x times x equal to 64. Since s, y, z, they are the same, I can replace y with x and replace z with x. I have s cubed equal to 64. That means s must be 4. And since s, y, z, they are the same, I must have s equal to 4, y equal to 4, and z equal to 4. That's the potential maximum or minimum. That's the potential maximum or minimum point. Then we plug in point 444 into the objective function. I plug in point 444 into the objective function. If I plug in 444, 4 times 4 is 16, 4 times 4 is 16, 4 times 4 is 16, 2 times 16 is 32. So I get 32 plus 32 plus 32 is 96. If we only get one value, how do we know if this is a maximum or minimum? Let's find a test point under the same constraint. Let's find a test point that satisfies the same constraint. Let's try to find syz. Let's multiply to be 64. Let's find a test point that satisfies the same constraint. We can try to find 2 times 4 times a. 2 times 4 is a times a is 64. So I can let s equal to 2, y equal to 4, z equal to a. So I can pick test point to be 2, 4, a. If I plug in 2, 4, a for syz, 2 times 4 is 8, 2 times a is 16. 2 times a is 16, 16 times 2 is 32. 4 times a is 32, 32 times 2 is 64. So we have 16 plus 32 plus 64. 16 plus 32 is 48. 48 plus 64 is 112. This is larger than 96. This is larger than 96. That means 96 at 444, 96 must be the absolute minimum. So the minimum surface area is 96. the minimum surface area is 96. And it occurs when SYZ equal to 4. So the dimension is length equal to 4 centimeter, width equal to 4 centimeter, and the height equal to 4 centimeter. That's the dimension of the box for which the surface area is a minimum. Number 6. Find the extreme value of f of sy. Extreme value means either the maximum or the minimum. So find the extreme value of f of sy equal to s squared plus 2y squared minus 2x plus 3, subject to the constraint s squared plus y squared less or equal to 10. This constraint looks a little different than the others. The other constraint is in the form of s comma y equal to k. And this constraint is an inequality. For Lagrange multiplier, the constraint must be a level surface. If the constraint is an inequality, we can use Lagrange multiplier. Then how do we solve this problem here? Now, let's consider this problem in 2 steps. First of all, I can find the partial derivative for f sub x and f sub y. Then set equal 0. Find the critical point inside the circle. Set equal 0. Find critical points inside the circle. And the critical points are the potential maximum and minimum points. Critical points are potential maximum or minimum points. So we can find all critical points inside the circle. Now, for critical point on the circle, I can set g of sy equal to s squared plus y squared equal to 10. For the critical point on the circle, I can set s squared plus y squared equal to 10. Then I can use Lagrange multiplier. To find the critical point on the circle. So take 2 steps. We first of all find the partial derivative. Set equal 0, find critical points inside the circle. Then we set s squared plus y squared equal to 10. Use Lagrange multipliers to find critical point on the circle. So first of all, I find the partial derivative. F sub x is 2x minus 2. F sub y is 4y. Set each of them equal to 0. Solve for x and y. Here I get y equal to 0, s equal to 1. So the critical point is 1, 0. This point lies inside the circle, so it counts. That's a potential maximum or minimum point. It's here. It's inside the circle. It counts. Next, we set s squared plus y squared equal to 10. Then we present this circle here. Now I can use Lagrange multipliers to find critical point on the circle. Next, apply Lagrange multiplier. Set gradient of f equal to lambda times gradient of g. Gradient of f we just found is 2x minus 2 and 4y equal to lambda times gradient of g. Gradient of g is 2x and 2y. If I simplify this, it can be rewritten as 2x minus 2 equal to 2 lambda x. 4y equal to 2 lambda y. The constraint equation is s squared plus y squared equal to 10. Then we can solve these 3 equations for 3 unknowns. What should we do first in order to solve the system of equations? If I multiply first equation by y, I can make 2 lambda sy on the right side. If I multiply second equation by x, I can also make 2 lambda sy on the right side. So both equations will have the same on the right side. Let's multiply first equation by y. I have 2sy minus 2y equal to 2 lambda sy. If I multiply the second equation by x, I'll have 4sy equal to 2 lambda sy. Then both equations will have the same thing on the right side. Then I can set the left side equal to each other, which means 2sy minus 2y equal to 4sy. If I subtract 4sy from both sides, I have negative 2sy minus 2y equal to 0. Subtract 4sy from both sides. Then I can factor pull out negative 2y. If I pull out negative 2y, I have x plus 1. Then solve the equations. I have y equal to 0, s equal to negative 1. When y equal to 0, I can substitute 0 into the last equation, solve for x. So s squared equal to 10. S equal to plus minus radical 10. If I substitute negative 1 for x, I can solve the equation for y. I have 1 squared plus negative 1 squared plus y squared equal to 10. Negative 1 squared is 1. Subtract 1 from both sides. Y squared equal to 9. Take square root. Y equal to plus minus 3. So we have 4 potential maximum minimum point here. Negative radical 10, comma 0. Positive radical 10, comma 0. Negative 1, comma 3. Negative 1, comma negative 3. And also, when we test for maximum minimum, we must include the critical point here. When we test for maximum minimum, we must include the critical point inside the circle. This inequality including everything inside the circle. This constraint including everything inside the circle. So we must include the point 1, 0 when we calculate maximum and minimum points. Now, sy is 1, 0, negative radical 10, 0, positive radical 10, 0, negative 1, negative 3, negative 1, positive 3. Those are the potential maximum or minimum points. Plugging each point into function f. Plugging each of these points into function f. Here I use my calculator. I get, when I plug in 1, 0, I get 2. When I plug in negative radical 10, 0, I get 13 plus 2 radical 10. When I plug in radical 10, 0, I get 13 minus 2 radical 10. When I plug in negative 1, negative 3, I get 24. When I plug in negative 1, positive 3, I also get 24. And I use my calculator. 13 plus 2 radical 10 is about 19.32. When I plug in 13 minus 2 radical 10 in my calculator, I get 6.67. So the largest is the absolute maximum and the smallest is the absolute minimum. Here we can see that the absolute minimum is 2 and the absolute maximum is 24. Under this constraint, the absolute minimum is 2. Absolute maximum is 24. So far, for problems number 1 through 6, every problem has only one constraint. But that's not always the case. Sometimes, in some problems, there are more than one constraint. Next, I'll show you how to find the maximum and minimum value of a function with 2 constraints. Now, let's look at the maximum and the minimum value of a function with 2 constraints. Let f of syz be an objective function. let g of syz equal to k and h of syz equal to L be two constraints. If we consider g of syz equal to k and h of syz equal to L as level surfaces, then their intersection will be a curve. Let curve C be the intersection of two constraints. Let C be the intersection of the level surfaces. G of syz equal to k and h of syz equal to L. So let curve C be the intersection of two constraints. Next, let me remind you one thing you learned in section 11.6. In section 11.6, we know that suppose there is a surface, suppose there's a level surface f of syz equal to k. Suppose there's a surface, let's call this level surface, f of syz equal to k. Then for any curve C on the surface, suppose this curve C lies on the surface. So let f of syz equal to k be a level surface. And let C be a curve lies on the surface. Then every point for all points P on C, for all points P on C, the gradient vector of F, is always perpendicular to the tangent line at P. The gradient vector of F is always perpendicular to the line that tangent to curve C at point P. Then for all points P on C, the gradient vector of F is always perpendicular to the line that tangents to C. At point P. For any point P on the curve C, the gradient vector of F always perpendicular to the line that tangent to the curve, that tangent to C at point P. That's what we learned in section 11.6. Since C is the intersection of the level surfaces G and H, then curve C lies on both level surfaces G of Sy G equal to K and H of Sy Z equal to L. Since C lies on both surfaces, then since curve C lies on both level surfaces, G of Sy Z equal to K and H of Sy Z equal to L, then for all point P on C, gradient vector of G and gradient vector of H are perpendicular. They are both perpendicular to the line that tangent to C at point P. So, since curve C lies on the level surfaces of G of Sy Z equal to K, then for any point P on C, gradient vector of P gradient vector of G must be perpendicular. It must be perpendicular to the tangent line at point P. Also, since curve C lies on the level surface of H of Sy Z equal to L, at point P, the gradient vector of H must be perpendicular to the tangent line at point P. So at point P, the gradient vector of G must be perpendicular to the tangent line. And at point P, the gradient vector of H must also be perpendicular to the tangent line. And we know that two vectors determine a surface. Two vectors determine a surface. So we have two vectors, and they determine a surface. These two vectors determine a surface that perpendicular to the tangent line. Let's call this surface S. Let's call this plane M. Let's call this plane M. Two vectors determine a plane. Two vectors determine a plane, and this plane perpendicular to the tangent line at P. Since both gradient of G and gradient of H perpendicular since both gradient of G and both gradient of H perpendicular to the tangent line at P, they determine a plane that perpendicular to the tension line. At P. And let's call this new plane M. They determine a plane M. Let's call this new plane M. And also keep in mind that this idea works for all point P. This idea works for all point P on curve C. This idea works for all points P on curve C. Next, let's look at function f. If I set f of s, y, z equal to c, and let c equal to different values, I will have different level surfaces. And we know that the maximum and the minimum of f the maximum and minimum of f occurs when the level surface f of s, y, z equal to c tangent to the curve C. Here, this C and this C is not the same thing. This C is the level surface of C. C represents some values. This C is capital C, represent the curve of C. So the maximum and the minimum value of f occurs when the level surface tangent to the curve C. Now let's assume the level surface f of s, y, z equal to C and the curve C, they tangent to each other at point P. If a surface and a curve they tangent to each other at point P, that means at point P, the line that tangent to the curve at point P must lie on a plane that tangent to the surface at point P. So assume the level surface and the curve, assume they tangent to each other at point P. Then at point P, the line that tangent to curve C must lie on a plane, that tangent to the level surface f of s, y, z equal to C at point P. Now, if a line lies on a plane, then the line must be perpendicular. The line must be perpendicular to the normal vector of the line of the plane. If we have a line light on the plane, then the line on the plane must be perpendicular to the normal vector. If a line light on a plane, then the line must be perpendicular to the normal vector. Now, since the normal vector of the plane let tension to the level surface f of syz equal to c is the gradient vector of f. Since the normal vector of the plane, the tension to the level surface, f of syz equal to c, is the gradient of f, then gradient of f is perpendicular the gradient of f is perpendicular to the line. Let tension to curve C at P. Since the normal vector always perpendicular to the line on the plane, and we know the tension line lies on the tension plane, then we know that the gradient vector, which is a normal vector, is perpendicular to the line, the tension to the curve C at point P. So know that gradient vector of f also perpendicular to this tension line. Gradient vector of f also perpendicular to this tension line. Therefore, gradient vector of f must lie on plane M. Therefore, gradient vector of f must also lie. Therefore, gradient vector of f also lies on plane M. Gradient vector of f also lies on plane M. Since the entire plane perpendicular to the tension line, and gradient vector of f also perpendicular to the tension line, then gradient vector of f must lie on this plane. Since this plane is determined by gradient vector of h and g, since this plane is determined by gradient vector of h and g and h, since this plane is determined by the gradient vector of g and h, then since plane M is determined by gradient vector g and h, then every vector in the plane, we can write it as a linear combination of g and h. Since this plane is determined by vectors g and h, then for every vector in the plane, we can write it as a linear combination of g and h. Therefore, gradient of f, we can write it as a linear combination of g and h. We can write it as lambda 1 times gradient of g plus lambda 2 times gradient of h. And these two scalar, lambda 1, lambda 2, they are called Lagrange multipliers. These two scalar, lambda 1, lambda 2, they are called Lagrange multipliers. Next, let me introduce the method of Lagrange multiplier for two constraints. To find the maximum and the minimum value of f of syz subject to two constraints, g of syz equal to k and h of syz equal to l, we need to solve the equations. Gradient of f equal to lambda 1 times gradient of g plus lambda 2 times gradient of h. The reason we are solving this equation is because at the maximum and the minimum point, the gradient of f must lie on a plane that determined by gradient of g and gradient of h. Therefore, at the maximum and minimum point, it must satisfy that gradient vector of f equal to the linear combination of gradient of g and gradient of h. The reason I'm solving these two constraints is because at all maximum minimum point, they must satisfy both constraints. At all maximum minimum point, the point must satisfy both constraints. So solve these three equations together for the potential maximum and minimum points. Then substitute the answer into function f. The largest is the maximum value and the smallest is the minimum value. Now, if there are n constraints, we solve the equation gradient of f equal to lambda 1 times gradient of g1, assuming that g's are constraints. We solve the equation gradient of f equal to lambda 1 times gradient of g1 plus lambda 2 times gradient of g2 together lambda n times gradient of gn together with all constraints. Solve all equations together for potential maximum and minimum points. Then substitute all solution into function f for maximum and minimum. The largest is maximum, the smallest is minimum. Next, let's look at some example that has two constraints. First example, find the extreme value of f of sy that equal to s squared plus y squared plus z squared. Subject to both constraints. S squared plus y squared equal to 1 and x plus y plus z equal to 1. So when we try to find the maximum and minimum value of a function with two constraints, we use Lagrange multiplier. Gradient vector of f equal to lambda 1 times gradient of g plus lambda 2 times gradient of h. Usually we call the first constraint g. We call the second constraint h. So use Lagrange multiplier. Let's first of all find a gradient vector for f. Gradient vector of f is 2x, 2y, 2z. Then take lambda 1 times gradient vector of g. Gradient vector of g is 2x, 2y, 0, then plus lambda 2 times the gradient vector of h. Gradient vector of h is 1, 1, 1. Then if I simplify, I can rewrite each equation as 2x plus 2 lambda 1, 2x equal to 2 lambda 1 x plus lambda 2. Second equation can be rewritten as 2y equal to 2 lambda 1 y plus lambda 2. The third equation can be rewritten as 2z equal to lambda 2. And together with two constraint equations, we have x squared plus y squared equal to 1. S plus y plus z equal to 1. We have four equations with we have 5 equations with 5 variables. We have 4 equations with 5 unknowns. We can solve the system of equations for these unknowns. Let's observe the first 2 equations. If I take the first equation, subtract by the second equation, then lambda 2 get cancelled. If I take the first equation, subtract by the second equation, then lambda 2 get cancelled. I have 2x minus 2y on the left side. 2 lambda 1x minus 2 lambda 1y on the right side. Lambda 2 get cancelled. Next, I can move everything to the left side. I have 2x minus 2y minus 2 lambda 1x plus 2 lambda 1y equal to 0. Then there are 4 terms. I can factor by grouping. Group first 2 terms together, I can pull out 2. And group the third term and the fourth term together, I can pull out negative 2 lambda y, negative 2 lambda 1. I have x minus y. Then factor again. I have x minus y times 2 minus 2 lambda 1. Then separate the equations. Solve for the first one. I have s equal to 1, s equal to y. And solve for the second one, I have lambda 1 equal to 1. Solve for the equation, I get sy equal to s equal to y, and lambda 1 equal to 1. When s equal to 1, when s equal to y, I can plug in x into the fourth equation here. Plug it into the constraint of g. Plug in s equal to y here. I have y squared plus y squared equal to 1. That means 2y squared equal to 1. Y squared equal to a half. Y by itself equal to plus minus 1 over radical 2. Since s equal to y, I have when y is, since s equal to y, when y is 1 over radical 2, s is also 1 over radical 2. When y is negative 1 over radical 2, x is also negative radical 1 over 2. Then I can plug in s and y and solve for z. I can plug in s and y here, solve for z. If I plug in s and y, I have 1 over radical 2 plus 1 over radical 2 plus z equal to 1. Let me solve the equation here. One over radical 2 plus 1 over radical 2 plus z equal to 1. I have 2 over radical 2 plus z equal to 1. 2 over radical 2 is radical 2. Solve for z. Z is 1 minus radical 2. So solve for z. Z is 1 minus radical 2. And for the other part, I plug in s and y here. Solve for z. I have negative 1 over radical 2 minus 1 over radical 2 plus z equal to 1. Let me solve an equation here. Negative 1 over radical 2 minus 1 over radical 2 plus z equal to 1. That means negative 2 over radical 2 plus z equal to 1. 2 over radical 2 is radical 2. So solve for z. Z is 1 plus radical 2. Let me put it here. Z equal to 1 plus radical 2. Next, when lambda 1 equal to 1, if I plug in into the first equation, when lambda 1 equal to 1, if I substitute in the first equation, I have 2x plus 2x equal to 2x plus lambda 2. When lambda 1 equal to 1, I plug in 1 here for lambda 1. I have 2x equal to 2x plus lambda 2. Subtract 2x from both sides. I get lambda 2 equal to 0. If I substitute 0 for lambda 2 here, I have 2z equal to 0. So z is 0. When z is 0, I can substitute z into the last equation here. I have x plus y plus 0 equal to 1. I plug in z into the last equation. I have s plus y plus 0 equal to 1. So s plus y equal to 1. If I solve for y equal to 1 minus x, then I can substitute y into the fourth equation here. Replace y with 1 minus x. I have x squared plus 1 minus x squared equal to 1. Solve this equation. I first of all expand the perfect square. I get 1 minus 2x plus x squared equal to 1. Expand the perfect square. Combine like terms. I have 2x squared minus 2x plus 1 equal to 1. Subtract 1 from both sides. I have 2x squared minus 2x equal to 0. Then I can factor pull out 2x. I have x minus 1. Solve this equation for x. I have s equal to 0 and s equal to 1. When s equal to 0, I plug in 0 here. I can find y. Y is 1 minus 0, which is 1. When s equal to 1, I plug in to find y. Y equal to 1 minus 1, which is 0. And in both cases, we know that z is 0. For both cases, z is 0. So we have a potential maximum minimum point here is 0, 1, 0. The other point is 1, 0, 0. And for these 2 points here, we have s equal to 1 over radical 2, y equal to 1 over radical 2, z equal to 1 minus radical 2. And here s equal to negative 1 over radical 2, y equal to negative 1 over radical 2, z equal to 1 plus radical 2. So here we have 4 potential maximum minimum points. We plug in each of the point into function f and find out what's the maximum, what's the minimum. We plug in each point into function f and find out what's the maximum, what's the minimum. Let me plug in here. First point, 1 over radical 2, 1 over radical 2, 1 minus radical 2. Second point, negative 1 over radical 2, negative 1 over radical 2, 1 plus radical 2. The third point, 0, 1, 0, 1, 0, 1, 0, 0. Then let's compute f of s, y, z. Here I use my calculator. In my calculator, when I plug in 1 over radical 2, 1 over radical 2, 1 minus radical 2, I get 4 minus 2 radical 2. When I plug in negative 1 over radical 2, negative 1 over radical 2, 1 plus radical 2, I get 4 plus 2 radical 2. When I plug in 0, 1, 0, when I plug in 0, 1, 0, I get 1. 1, 0, 0, I also get 1. So use my calculator. 4 minus 2 radical 2 is about 1.17. 4 plus 2 radical 2 is about 6.82. Then the largest is absolute maximum. The smallest is absolute minimum. So the absolute minimum is number 1. The maximum is 4 plus 2 radical 2. The maximum is 4 plus 2 radical 2. So that's the answer here. Next example, find the extreme value of f of s, y, z equal to 3x minus y minus 3z, subject to both constraints, s plus y minus z equal to 0, and s squared plus 2z squared equal to 6. So here, f of s, y, z is an objective function, and we have two constraints. Usually we call the first constraint g of s, y, z, and we call the second constraint h of s, y, z. Then we can use Lagrange multiplier to solve this problem. Gradient vector of f equal to lambda 1 times gradient vector of g plus lambda 2 times gradient vector of h. Let's first of all find the gradient vector of f. Gradient vector of f is 3, negative 1, and negative 3 put in column, equal to lambda 1 times gradient vector of g. Gradient vector of g is 1, 1, negative 1 put in columns, plus lambda 2 times gradient vector of h. I have 2x, 0, and 4z. Simplify each equation. I have 3 equal to lambda 1 plus 2 lambda 2x. Negative 1 equal to lambda 1 plus 0. Negative 3 equal to negative lambda 1 plus 4 lambda 2z. Then I combine two constraints together with these three equations. I have x plus y minus z equal to 0, s squared plus 2z squared equal to 6. Then solve these 5 equations for 5 unknowns. We have 5 equations and 5 unknowns. The simplest one is the second one. Lambda 1 equal to 1. Lambda 1 equal to negative 1. So I can substitute lambda 1 into the first equation and the third equation. I have 3 equal to negative 1 plus 2 lambda 2x. That can be rewrite as 4 equal to 2 lambda 2x. If I divide both sides by 2, 2 equal to lambda 2x. If I plug in lambda 1 into the third equation, I have negative 3 equal to 1. Negative is positive 1 plus 4 lambda 2z. I can subtract 1 from both sides. Negative 4 equal to 4 lambda 2z. Then I can divide both sides by 4. Negative 1 equal to lambda 2z. Now let's observe these two equations. If I keep the first equation the same, I multiply this equation by 2. I have negative 2 equal to 2 lambda 2 times z. Then if I add them up, I have 0 equal to lambda 2x plus 2 lambda 2z. Then I can factor, pull out lambda 2. If I pull out lambda 2, I get x plus 2z. Then solve this equation. That means we either have lambda 2 equal to 0 or s equal to negative 2z. When lambda 2 is 0, is it possible? If lambda 2 is 0, then 0 times x must be 0. So that's impossible. If lambda 2 equals 0, we have 0 times x. It cannot be 2. So that's impossible. 0 times x won't be 2 if lambda 2 is 0. So that's impossible. Lambda 2 won't be 0. Otherwise, 0 times x, it won't be 2. Then that means x must be negative 2z. If I substitute negative 2z for x here, if I replace x with negative 2z, I have negative 2z squared plus 2z squared equal to 6. Negative 2z squared is 4z squared plus 2z squared equal to 6. And that means 6z squared equal to 6. So z squared must be 1. Z is either positive 1 or negative 1. And when z is positive 1, x is negative 2 times z, x is negative 2. When z equal to negative 1, x is negative 2 times negative 1, which would be positive 2. So when z is negative 1, x is negative 2. When z is positive 1, x is negative 2. When z is negative 1, x is positive 2. Then, once I know x and z, I can substitute here, solve for y. Once I know x and z, I can substitute here, solve for y. So I substitute 1 for z, negative 2 for x. Negative 2 plus y minus 1 equal to 0. Negative 2 plus y minus 1 equal to 0. So y equal to positive 3. If I substitute negative 1 for z, substitute 2 for x, I have 2 plus y minus negative 1 is plus 1 equal to 0. So y equal to negative 3. That means we have two potential maximum minimum point. Negative 2 3, and 1. Positive 2, negative 3, and negative 1. We have two potential maximum minimum points. Next, we try to plug in the point to find the absolute maximum and absolute minimum. Next, we plug in the point S, Y, Z. First point is negative 2, 3, 1. Second point is 2, negative 3, negative 1. Plug into function of f of s, y, z. Function f of s, y, z is 3x minus y minus 3z. Then plug in. And I use my calculator. I get negative 12 for the first point, positive 12 for the second point. That means my absolute maximum is positive 12. My absolute minimum is negative 12.